Okay, so in the first lecture of the course, I present an introduction on hydrology, definition of hydrology, etc. And today I want to enter into the practical issue of water resources management, just a brief introduction to water resources management. And first of all, let me concentrate to give you an idea on the total amount of water availability over the Earth. And this slide serves to give you an overview on the amount of the total amount of water that we have at disposal. And then in the next slides I will present some concepts related to the hydrological cycle. So you see that over the Earth, the great majority of the water is salt water. Is more than 95% of all water over the Earth is salt water. And of this 95.5%, we have that almost all the water, almost all the salt water is contained in the oceans. But we have some salt water also in groundwater and lakes. This is a big problem. When we have salt water in groundwater, this is a big problem, because usually it means that from the oceans, from the seas, you have some infiltration of salt water into the land, underground. And this is usually a problem. It's a big problem. Why? Because if you dig a well in the ground to get some water from the underground, and this is one of the most important ways to secure water to people, take water from underground. And when you try to take water from underground, if you find salt water, of course it's a big problem because it's not fresh water. And usually the intrusion of salt water is also provoked by humans when they extract water from the underground. If you have a situation like this, if you have a situation like this, like a land that goes into the ocean, this is the sea. Usually, from the mountains, you have an inflow of underground water which goes downstream, which originates the presence of a saturated zone. This saturated zone is limited, it's bounded by the water table. This is the water table. It's upper bounded by the water table. And you see that the water table is declining downstream. Why it is declining? It is declining because this means that the water, the underground water, is moving downstream and entering into the oceans. I mentioned last week to you that we have typically a flow of groundwater from the land to the oceans. And again, let's concentrate on the fact that the slope of the water table is inclined downstream, so it goes it loses some altitude by flowing downstream, because in this way the water takes the energy to flow in the underground. By decreasing its altitude, the water transforms potential energy to kinetic energy, and therefore can take the energy to move. So you can understand from this very simple consideration that if you have water in the underground that moves downstream towards the oceans, you have a water table that slopes down downstream. So this is a typical situation. Now, let's assume that you dig a well here. I'm not sure the pronunciation is correct. In Italian we say pozzo. It is written, I think in English it is written like so. Means that you dig a hole to extract water. I'm not sure if there is an H here. Not sure. Right. But in any case, I hope you understood the term and the concept. Now, if you dig the swell here and you extract water, what happens is that you decrease the altitude of the water table. So you pass to a situation which is like so. This is the situation, because you lower the level of the water table. Of course, the amount of the decrease of the altitude, the amount of which you lower the level of the water table, depends on the flow of water that you extract. The more you extract water, the more you lower down the water table. Now, if you get to such a situation, of course you can have an intermediate situation. You can have a situation like this. So you have a increasing decrease of the water table once that you extract water. The more the water that you extract, the more the altitude of the water table gets decreased. Now, if you get to an extreme situation like the lower one that I depicted here, what happens? You see that the water table, the level of the water table is declining from the ocean to the underground, to the land, sorry. It's declining from the ocean to the land, which means that you have a flux of water from salt water from the ocean to the land. So once that you extract the water from the underground, we should always be careful not to lower the altitude of the water table below the sea level. Otherwise, we induce an intrusion of salt water. This is called salt water intrusion, which is a big problem. This must be avoided, because once that you get some salt inside here, it's very difficult to remove it. And once that a wheel gets salted, very often we have to leave it, to abandon it. So this is a big problem. And you see that we have some significant percentage of salted groundwater. And in many cases, as I said, this is a consequence of human exploitation of groundwater. This is, again, a relevant problem. Okay, now let's concentrate on the fresh water. What we call fresh water is the water that is good for us to use, which is available for civil use, for agriculture, etc. Keep in mind that the salt water is practically useless. You can't use it for drinking, of course, you can't use it for irrigation, and also it's very difficult to use salt water for industrial use, because if you use salt water to cool down industrial plants, then, you know, the plants get salted, the salt remains on them.
Quindi tutti i pozzi che sono in Emilia Romagna, che ce ne sono miliardi, sono soggetti all'intrusione di acqua salata? Possono essere soggetti?
See, the question is, we have many wells in Emilia Romagna region, in the Padana plain, with many of them, which are the main source of fresh water for civil use, industrial use, irrigation, etc. And she asked if there is the risk for intrusion. My reply is, if you are close to the sea, yes, and some of them already get salted. Of course, if you get very far from the sea, then the problem is less pronounced, because the travel of the salt water into the land requires, you know, once that the water travels in the underground, the altitude of the water table, of course, decreases, because you need energy. So if the well is located very far from the sea, in order to have enough energy for the salt water to get to the well, you need really to lower down very much the water table. So the problem is more pronounced close to the sea, but yes, close to the sea, even in the Emilia-Romagna region, we have problems. And in fact, we are trying now, and we tried in the past, to get alternative sources of fresh water, not to use much the water from the underground for this problem. Okay, let's now concentrate on the fresh water. So again, salt water is practically useless. The only significant use that you can make of salt water is through desalination. Desalination, which means that you get the salt water and you take the salt off. The problem of desalination is that it's very costly, and it's also requires industrial plants, requires a lot of energy, and it's a bit slow also. So the only possible significant use of salt water is desalination. Okay. Now, let's concentrate on the fresh water. The fresh water is only 2.5% of the total water available. And the great majority, 70% of this 2.5% is stored in glacier or permanent snowpack and permafrost. So basically it cannot be used. You need to melt it to use it. Now let's go back to groundwater. Let's go to groundwater. Groundwater is 30% of 3%, so it's about 100% of the total water on the earth. I'm talking about not salted groundwater, groundwater which is available as fresh water, and this is our main source of fresh water. This explains why I said that groundwater is a very important source of fresh water for us, of course, because it's the most significant. Then we have some water, very reduced percentage. You see about 1 over 100, so 2 orders of magnitude less. We have some water stored in lakes. Again, 2 orders of magnitude less than groundwater. Lakes includes artificial reservoirs. Again, keep in mind, 2 orders of magnitude less. Then we have soil moisture, which cannot be used, but is still significant. Soil moisture is included in a belt of soil which is just above the saturated zone. So below the water table you have the saturated zone. Above the water table the soil is unsaturated, but you have a belt of soil which is called unsaturated zone, which means that you have some moisture there, we have some water, you have some water, but the soil is unsaturated. This is a very important layer of soil. I think layer is a more correct term than belt. Belt is, layer. You have a layer of soil that is humid, but it's unsaturated. It's also called Vaduz zone. And it's very important because in the unsaturated zone you have transport processes of water from the surface and the groundwater. So it's very much important to study how water flows in this layer of soil, which is complicated. Because if the soil is completely dry, the upper zone usually is dry soil, it's quite easy to understand how water moves, and also the dry soil, it's less important than the unsaturated zone, because in the unsaturated zone you find the roots of the trees and the roots of all the plants that form the ecosystems. So the unsaturated zone is a reservoir of water which is important, even if we cannot directly use it. And again, to describe the movement of water in the unsaturated zone is difficult, because if the soil is saturated, it's relatively easy to model the water flow. If it is dry, it's relatively easy. If it is unsaturated, the dynamics of the movement depends on the humidity, on the level of humidity. So it's difficult to describe it. And this explains why there is a branch of hydrology which is called Vaduz zone hydrology. They are studying explicitly how water moves in the unsaturated zone. Okay, and let's also think that, let's keep in mind that when you talk about agriculture and then there is irrigation, then you are talking about unsaturated zone, Vaduz zone. Okay. Atmosphere. In the atmosphere we have some water, which we cannot directly use. There are some cases in which people devised the mechanisms to take the water from the atmosphere by inducing condensation. And for instance, there are techniques for catching the fog. In practice, they try to favor the condensation of the fog and in general the humidity of the atmosphere around bodies like metal bodies which are colder, and then the water flows along, the condensed water flows along this body, this capturer, and is collected by humans. But these are really very rare examples. When people really find it difficult to secure water, they devised also methods for catching the water from the atmosphere. Rivers are, as groundwater is, very much important. The percentage is reduced, but usually rivers are important. Why? Because it's the source of water which is easier to take, easier to use, because it's surface water. It's very easy to take water from the rivers. And this is the reason why ancient civilizations started by using the water from the rivers. They built the cities around the rivers. If you look at a city, you can find a city which is not around a river. At least an old city. Maybe now you can find some cities also in the middle of a desert, but in ancient times, old cities always were built along rivers. And then we have some water in the biosphere, which is something in Italian is biosphere, which is a part of the atmosphere, and or let's say, no, sorry, the definition is biosphere means the collection of all living bodies. So you have also water in living organisms like humans, like plants, and this is the biosphere. Sorry, I give a wrong definition at the beginning. But this is very reduced, of course. Even if you see that it's comparable to water in rivers. So, again, let's concentrate from now on groundwater and rivers. The water cycle or hydrological cycle. Now, I think that you all have an idea of how the water cycle works. And in principle, we all know that because we studied in the primary school and we were taught the water cycle since we were children. The problem is that if we look at the details, the situation becomes much more complicated. We all know that water evaporates and goes in the atmosphere, and in the atmosphere the evaporated water moves from the oceans, where we have the majority of the evaporation, to the mountains, where the evaporated water finds a cooler atmosphere, and then cooling favors the condensation of water in clouds, and then the water rains or snows and reaches the earth. And we were told that by flowing over the earth or in the underground, the water goes back to the ocean, and also some evaporation is of course possible from the lands. So basically this is a well-known concept, but if we look at the details, the situation becomes much more complicated to the extent that we still don't know many of these details. So many of these details of the water cycle and the hydrological cycle are still not known. We ignore them. And this is the reason why there is a so intense research activity in hydrology, because humans are trying to better understand what happens to water, and I mentioned to you that we still don't know how the water flows from the time in which it lands in the form of rain over the earth, from the time it gets in the rivers, when we can see there is some time elapse, some time delay during which the water, of course, flows downstream, and we still don't know how this flow occurs. This picture gives to you some of these details, and what is important for us to understand from this picture, to fix in this picture, is, first of all, the complicated mechanisms of water flowing along the hill slope. You see here a separation between surface runoff and infiltration. And then infiltration, you see that there is a contribution to the downstream flow called percolation. Percolation is water flow in the immediate proximity of the Earth's surface, and this percolation can occur in the vertical direction, but also there can be a component in the horizontal direction. This flow occurs downstream. So it may happen that some of the water comes back to the Earth's surface in the form of springs, for instance, just after a reduced percolation. We know that there are some springs that react to rainfall very quickly. Like after 1 hour that rainfall started, we see some springs activating, which means that these springs are fed by percolation. And it's also called near surface flow. Then we have some deep infiltration, which originates soil moisture and the presence of a water table. And then there is a groundwater flow. And also there is a component of deep percolation, which is not shown here, which means that a very reduced amount of water goes towards the Earth's interior and doesn't come back to light immediately. It may come back, but maybe after 200 years. It's deep percolation. So this is one of the things that we have to focus here. The very complicated mechanisms that govern the groundwater flow. The second very important thing that we have to focus on this picture is water management. And it's not emphasized enough here. Sorry, it's not emphasized enough. Meaning that water management is becoming a very important component of the water cycle, at least in some sides of the Earth, not everywhere. The great majority of the Earth is still not urbanized. It's still not, let's say, modified by humans. Only a reduced part of the Earth is modified by humans. But in those modified parts, which are the most important for humans, because humans live there, in those modified parts, the water management is interfering abruptly, very significantly, with the hydrological cycle. And this is one thing that needs to be carefully considered. Because, you know, classical hydrology always tried to understand how the water cycle works in pristine condition. Pristine means virgin condition, not impacted by human. And then, once the objective was first to get an understanding of how it works in pristine conditions, and then estimate the amount of water available for human use. This approach ignores that the presence of humans affects the conditions, and therefore water availability can be heavily influenced, meaning that if we just study the catchment in pristine condition and we include water management afterwards, we ignore the fact that water management can have an influence on evaporation, rainfall, infiltration. So now, modern hydrology has focused on this very important issue. Humans are part of the system. Water resources management, water management in general, is part of the system. We cannot ignore that there is a human impact. And I give to you a very simple example. Let's suppose that you you estimate the amount of water that is available in a given site, groundwater, and then you realize that there is not enough groundwater. Like, I'm lacking 10 millions of cubic meters per year of water. Then the idea could be I go upstream and I build a reservoir. And the size of the reservoir, you could design it by assuming that you lack 10 millions of cubic meters of water per year. But once that you built the reservoir, you could realize that the groundwater storage decreased because, you know, of course, you keep the water upstream and you reduce the infiltration downstream. So you may realize that the amount of groundwater that you now have at disposal is reduced. And you may realize that you don't need just 10 millions of cubic meters of water in the reservoir. You need 15 millions because the groundwater amount is decreased. If you ignored this fact, you would design an artificial reservoir that is not sufficient to cover your needs. Instead, if one tried, before designing the reservoir, to understand how groundwater is impacted by humans, by the reservoir, then one could realize that indeed the size of the reservoir needed to be bigger. Of course, the question is, how can I do it? This is still unsolved because, you know, usually when we build a reservoir, we may get an idea of the consequences of the impact of the reservoir on hydrology, but still we don't have the means to analyze in detail this impact. But still the concept must be kept in mind. We should always think about the impact of humans. Okay, let me now show you, this is not easy to read, but I'm explaining what it means. It's the same picture. You don't see anything different here. What is interesting to see here is the quantitative analysis. This gives to you an idea of the fluxes. I have another slide after this. And of course, you don't need to keep in memory the numbers. You just need to keep in mind the concepts. I may give you an example of a question that I could ask you at the examination about this kind of slide or concept. Okay, let me give to you later after I have explained this slide. So let's assume here that the precipitation of land is equal to 100, just to make a reference. And let's see what is the amount of the fluxes compared to precipitation on land. And evaporation from land is 63, which means that 63% of what rains on the land evaporates. And of course, it's not available for us to use. And keep in mind that this 63% can be impacted by humans. If you exploit agriculture and you increase irrigation, you automatically increase the evaporation. This is called blue to green water diversion, which means that you take some water from the underground or from the rivers, some fresh water, which is called blue water, and then you use it to irrigate the fields, which means that the water evaporates. So you have converted some fresh water in evaporation. This is an important thing. But in any case, let's keep in mind that evaporation is about 60–70%. Okay, evaporation from the ocean is 6–7 times the evaporation from the land. It's 424. So this is a question that I may ask you, like, give me an idea, the evaporation in the ocean is higher or lower than the evaporation in land? And of course you say higher, and I may say, okay, but 1 time higher, so just twice or 10 times, give me an idea. What is important, and I will be very pedantic on this, I will tell you many times, it is important that you put in your mind some orders of magnitude. Because, you know, when, for an engineer, orders of magnitude are very much important. And especially in a science like hydrology, which is affected by a very relevant uncertainty. So you make a calculation, you make an hydrological analysis, and you know that it's uncertain. And in order to give an evaluation of the results of your analysis, then you need some personal expertise, what is called expert knowledge. Because of course you have uncertainty, and then you should be able to check if the result of the analysis is reliable, is consistent. And this is usually done by using orders of magnitude. So for a designer, the knowledge of the orders of magnitude is very important, and also when you speak with your clients, it's very much important that you show, that you prove, that you have a good knowledge of the topic, of what you are talking about. And you can provide this if you know the orders of magnitude. And an example of very simple orders of magnitude, which I didn't know, personally I didn't know even after my PhD, how much is the rainfall depth in 1 year over Italy, on average. Just an order of magnitude is 10 centimeters, is 1 meter, is 10 meters. So it's very much important that you know that it's about 1 meter. So the amount of rain, the rainfall depth over Italy, let's say over this kind of latitude, 45 degrees in Europe, is about 1 meter. Of course, it depends also on the altitude. But if you take the average over Italy, it's about 1 meter. And it's also very much important to know that if you go in the south of Italy, you go to about 600. And if you go in the Alps, you may get as high as a couple of meters. So this is the order of magnitude. Another issue. I think you are familiar with the definition of water flow. The water flow is the volume of water that passes along a river per unit time. This is called, in many terms, many synonyms are used. And one is river flow. Another one is river discharge. I will provide for water flow quantitative definition later on. But just to give you an anticipation, it means, again, the amount of water that passes along the river at a given location per unit time. Usually is measured in cubic meters per second. Because, you know, volume, cubic meters, per unit time, second. But some people like to measure in different, this is the international system of measure, some people like to measure it in liters per second. Now, how much liters is 1 cubic meter? This is very much important to know. I tell you that this is one thing that even after my degree I didn't know. It's absolutely to avoid. If you speak with people that you don't know, you let them know that you don't know how much liters you have in a cubic meter. This is 1 cubic meter is equal to 1,000 liters. Another issue. This is an order of magnitude that is a bit more complicated. If one tells about the Po River, speaks about the Po River, it's what is the order of magnitude of the average river flow of the Po River at the closure, when the Po River gets into the sea. What is the average amount of water flow that the Po River delivers to the sea, to the Adriatic Sea? This is difficult to know. But it's important. If you go and speak with people working on the Po River and you design, for instance, a plant for getting water, a pumping plant for getting water from the Po River, and these people occur to know that you don't know what is the average flow of the Po River, this is very bad. And to give you an idea, but this is difficult, it's about it's about 1,500. So this is an example of orders of magnitude. So why I show you this slide? Just to give you some orders of magnitude, so that you know that evaporation from the ocean is about 7 times evaporation from the land. And of course you may say this is not really interesting. Yes, but if you are a water resources manager, I think it's interesting. Okay, other examples. If you have 100 is precipitation and 73 is evaporation, what remains is about 37. And you see here, it's difficult to read, but the total amount of water that flows from the lands to the oceans, including rivers and groundwater, is 38. Here it's written. Okay, and let me now go to the next one. Precipitation over the ocean is almost 4 times precipitation over the lands. Next one, this is seems to be more complicated, but it's not really complicated. But of course, you don't need to focus on all these fluxes, just on the main ones. And let me explain this slide. Let's assume now that total terrestrial precipitation, you see, it's 111. Typically, don't ask yourself what is the unit of measure of this 111. It's just a term of reference. So let's assume that this is 111. Now, you see that if you have 111, snowfall usually is 10% of rainfall. This is an order of magnitude. And the total amount of 111 falls 54 over the forests. Between parentheses, you see the extension of the forest in, it's given in, let me look on the slide because it's not clear. It's 10 to the power of 6 square kilometers. So you have an indication between parentheses of the extension, total extension over the earth of each single land use.